Good morning. Here am I again, coming to you from the Fairfield Marriott in New Jersey. And I'm using now the Fourier Transform and the inverse Fourier Transform to solve some circuit problems in electrical engineering. The Fourier Transform and the inverse Fourier Transform. But let's just review a couple of properties. We're going to use Ohm's law, V equals IR, and in the time domain, V of t is equal to I of t, R of t, and in the frequency domain, V of W equals Z of W, Z of omega, I of omega. Z is the impedance and I is the current. I will say for this now that R will remain the same, L will go to J omega L, and the capacitance C will go to 1 over J omega C. You're using the transfer function property to know that H of omega is equal to Y of omega over X of omega. Or X of omega is equal to H of omega, Y of omega. If Y is the output and X is the input, then we have to know that H of omega is equal to the output over the input, X of omega. And suppose if we take now a basic circuit now with resistance R and capacitance. And suppose for simplicity we make the capacitance 1 farad and the ohms, resistance 2 ohms. And here we have some sinusoid input voltage VI of t. Yeah, VI of t, some input voltage, and some output voltage V0 of t. And we're given now that the input voltage now VI of t is equal to 2e to the minus 3t unit step function u of t. So we say now that in the frequency domain VI of omega, this is in the time domain, would be equal to 2 over 3 plus j omega. Note the 2, the 3, and omega. And if we don't wish to work with the complex j omega, we could say now that S is equal to j omega. And then in our final calculation, we return the S equal j omega to j omega. S equal j omega. This is only for simplicity, but those who can work straight off with the complex j omega without making mistakes, they are free to do so. So we say now that H of omega was equal to V, the output V of omega over I of omega, and that will be equal to 1 over j omega over 2 plus 1 over j omega. And if we simplify that now by multiplying top and bottom by j omega, we have now that's equal to 1 over 1 plus j2 omega. So that now V0 of t would be equal now to 1 over 3 plus j omega times 0.5 plus j omega. And we use partial fraction for this now, and we get this to be equal to a over 3 plus j omega plus b over 0.5 plus j omega. And those of you who know your mathematics and to do your partial fraction, you will do that and see that we get as our a and b minus 0.4 over 3 plus j omega plus 0.4 over 0.5 plus j omega. And so then we use the inverse Fourier transform and say now that V0 of t is equal to 0.4 into e into 0.5t minus e to the minus 3t u of t. And that's the now solution for the circuitry using Fourier transform and inverse Fourier transform. So you could make up similar problems like these, with capacitance and RC circuits, resistance capacitance, and some RL and CL circuits with the inductance. But remember now that the inductance is the J omega L in the frequency domain. So let's try to do another one of these circuit analysis using Fourier transform and inverse Fourier transform.